Hello and welcome to this course on finding areas using definite integration. We can treat this as application of integration in real life. Before we begin, let's have a case study of the income gap between the rich and poor of a country. See, a boy is asking other friend that in some country there are very wide income gap between the rich and poor. What you say about that type of country? Definitely the wide gap between the rich and poor is not good for a country. So can we somehow predict how exactly the quantitative measurement of inequality between the income imbalance is? Well, this is very simple, and this is something where we can exactly apply the application of integration to quantify the income distribution of a country. To measure the inequality of a country and especially the income distribution of a country, we can make use of Gini coefficient. This is a very popular coefficient that can exactly predict the income distribution and income imbalance between the different members of a society. The Lorentz curve is sketched for various points on the curve, and the X% of the families are poorer and Y% of the total income of all the families in the society. Here the Gini coefficient is given by the area bounded by the Lorentz curve and the line L divided by the total area under the curve. See, this line is the line of equality. Ideally, this is where our society must fall in. But the Lorentz curve is something that lies below this line of equality. This is a curve, shows the x-axis as the cumulative percentage of the number of households, and the y-axis is representing the cumulative percentage of household income. This is one of the very fair application of integration, but before we apply the integration in real life, we must know how exactly integration can be applied to get the areas under the curve. Let's quickly start with finding the plane area using the integration. Area of the region bounded by a curve with the x-axis. See, we have seen that the definite area gives the algebraic area under the curve. That means the Riemann sum was the limit n approaches to infinity. I was starting from 1 and then going till all the way n, f zi delta x zi, where delta x was the width of the elementary strips we have considered it, and that was b minus a divided by n, and this was very small. When fx is greater than 0 for some interval a and b, this algebraic area is basically the area above the x-axis, and so is actually the actual area we wanted. So if we have a very thin rectangular strip drawn all the way here at the point zi, the height of the function is f zi and the strip is delta x, and so the area of this small strip is f zi multiplied by delta x, and when we sum up these strips all the way, we are going to get the area. So for fx greater than 0 in the interval a to b, the area is basically the definite integral, which was actually the algebraic area. So whenever the function is above x-axis, we don't need any special result, and this is how we can exactly get the areas under the curve. But this is not genuinely the case for every function. So what will happen when our curve goes below x-axis? Yes, when the curve goes below x-axis, the area bounded between the same point A and B is not exactly the definite integral. In fact, the actual area is negative of the definite integral, because the definite integral in this case will be a negative value and we want an actual area, so we just put a negative sign over there before the definite integral to get the final value. So when function is less than 0, we can say that between the point A and B where the function was negative, the actual area is given by minus of definite integral a to b fx dx. Pretty simple, isn't that? See the diagram here, this strip here is having a negative area because it is lying down the x-axis, and in that case the area is going to be negative. What if a function is having some portion of it above x-axis and some other portion below x-axis, and what exactly we'll be doing to get this area? Yes, this is very interesting and very useful. We must know it. Well, there is a very simple approach out there. We can just divide the whole function into two intervals, between a and c and between c and b, where c lies between the number a and b at which the function is changing its sign. That means before c the function was positive, while after c the function is negative. That way, dividing this integral into two pieces, we can say that the first area between a to c, which is definite integral a to c fx dx, is positive 1, while the second area is negative 1 because it is below the x-axis. And in that case, we can quickly find the actual area by the definite integral a to c fx dx minus definite integral a to b fx dx. Isn't that easy? Yeah. Let's now see a very simple and useful example here. Just to understand how exactly we are going to apply the idea that we have just learnt in action, let us see my example 1 here. We are having a function y is equals to x square, and we want the area bounded by this curve y is equal to x square, the x-axis and the line x equals to 3. Yeah, you can just pause the video and try it. Very right. Now you have tried, let us see how exactly we can do it. See, the required area is very simple, as the function is completely lying above the x-axis between this given interval x equals to 0 to x equals to 3. We can say that the area required is integral 0 to 3 x square dx. Let's quickly solve this integral. The integral of x square is x cubed by 3 and the lower limit is 0 and upper limit 3. So the area is going to be 9. Have you got the same answer? Very right. Let's now move to the second problem. Second problem is little more interesting. Reason is, it is going above x-axis in some interval as well as below x-axis in some other part of the interval. Well, find the area of the region bounded by the curve y is equals to x square minus 6x plus 8 and the x-axis in the interval 0 closed to 4. Don't bother about 0 closed and 4 because the boundaries are not going to give you any special area. That means if the problem would have been open interval 0 to 4, it is still the same. Okay, so before we begin, I want you to try this problem yourself. You can quickly pause and try it. Very right. Now you have tried. Let us check whether your answer is right or wrong. Fine. Let's talk about the solution of this problem. Here, x square minus 6x plus 8 is crossing the x-axis. That means some portion of this curve is below x-axis while some other portion is above x-axis. Can you identify the two portions? Yes, you are right. Between the point in the interval 0 to 4, there is some point in interval 0 to 4 at which this function is becoming 0. Before it was positive, and after that particular point this is negative. How to identify that point where this function was 0? Simple. We want x square minus 6x plus 8 equals to 0. This is a simple quadratic equation. Solving it, we are ending up with the two values of zeros. One is 2, other is 4. That means when x is equals to 2, this value is going to be 0, and when x is equal to 4, this is going to be again 0. The point where this function is 0 and which lies between 0 to 4 is 2. That means the intermediate value is 2. Before 2 our function is positive, after 2 and before 4 it is negative. So we can just divide the whole area into two pieces, and so the required value is the integral of 0 to 2, the same function x square minus 6x plus 8, and negative of the integral 2 to 4, the same function x square minus 6x plus 8. Remember, this negative sign is coming because the curve is below x-axis. Very right. Can you quickly simplify it further and give me the answer? Yeah, the integral of x square is x cubed by 3, while minus 6x is 3x square, while the 8 integral is 8x. Doing the integral between the interval 0 to 4, putting lower and upper values precisely, we are going to get 20 by 3 as the first integral, while minus 4 by 3 as the second interval. Finally, after doing a bit of calculation, we'll be ending up to the right answer, which is 8. Hope you enjoyed the calculation. Yeah? Fine.